Hello everybody, in this lecture I would like to provide a combinatorial proof for Fermat's Little theorem. Here is a view of this celebrated theorem. If p is a prime number, then for any integer a, the number a to the power p minus a is divisible by p. In the language of modular arithmetic, that would be the following statement. A raised to the pth power is congruent to a in mod p. Consider first the case when p is equal to 2. In this case, we would like to show that 2 divides a to the a square minus a, which is simply equal to a times a minus 1. But then it's obvious, regardless of the parity of a, if a is odd, then a minus 1 is even. As a result, it's divisible by 2. If a is even, then it's already divisible by 2. So this is obvious. So therefore, for the rest of the problem, I will be just considering p an odd prime. Okay, so let's continue with the rest of the proof now. Okay, so in order to prove this statement, I would like to consider the following problem. Consider the coloring of the vertices. So color the vertices of a p-gon of a regular, I should probably say regular, of a regular p-gon with a different colors. So you have a different colors to choose from, and we would like to color the vertices of our polygon with p vertices and p sides. However, the trick here is that I would like to only consider rotational symmetries up to rotations, meaning that two colorings will be considered the same if I can obtain one coloring from the other by a simple turning rotation of another coloring. So we are considering essentially different colorings of a p-gon, a regular p-gon, where we only consider up to rotation. So reflectional symmetries will not be considered. So let's start by drawing our regular p-gon, something like that. Okay, so this is vertex 1, 2, 3, and so on. So probably this vertex is p minus 1 over 2. This one is p plus 1 over 2. And then you have p minus 1, and so on. I hope the vertices are clear. So what I want to do next is to list. So I will apply a Burnside argument. I would like to make use of Burnside's lemma, or the Burnside lemma. For that, we need to figure out the group of symmetries, the rotational symmetries, the symmetric group G, and basically the elements of this group are basically the do nothing, the 0-degree rotation, or we can simply rotate it. We can a rotation by 2 pi over p degrees, right? It would take point vertex 1 to vertex 2, 2 to 3, 3 to 4, and so on, right? It will simply rotate each vertices to their adjacent neighbor. And then the other rotation would be 2 times 2 pi over p, and so on. Finally, p minus 1 times 2 pi over p. So in total, we according to the symmetry, when you consider the symmetry group of this shape, the regular p-gon, where p is a prime, this is it, right? So this is the group that acts on this shape. And now we can start finding the number of orbits, or the number of essentially different colorings, which is obviously an integer. That's the trick. So that would be equal to 1 over. So in this set, let me first write that. summed over all G in G, fix of G. Okay, so that was Burnside. So 1 over, here we see we have P elements, so 1 over P times, okay, so let's start with the fix of E. How many colorings will remain unchanged when I apply the do nothing symmetry here? If I do nothing, all the colorings will remain the same. How many different ways can I color vertex 1? A different colors, A different colors, A different colors. So each vertex by itself is a unique cycle. So in each one is A different colors. We have in total P cycles. Plus, now we are rotating by 2 pi over P. In that case, 1 will move to 2, 2 will move to 3, and so on. So there will be a unique mega cycle, a big cycle. And in total, there is A different ways to color this cycle, right? So because whatever color 1 is, 2 should have the same color, and whatever color 2 is, 3 should have the same color, and so on. Plus, now we need to rotate it by an angle of 2 times 2 pi over P, meaning that 1 will go to 3, 3 will go to 5, 5 will go, and so on. Eventually you will come back to P, and then P will go to 2, 4, blah blah blah, and then P minus 1, and eventually we will go back to 1, right? So in total, there's a big, again, unique cycle, well, a big yeah, just a unique cycle, because P is a prime. That's the main reason. So because there's a unique cycle, there's A different ways you can color that. And because P is prime, every single one of these rotations will just create this big unique cycle. So each one will have just A different ways. So the fix of G for all of these, except for the identity symmetry, it will be equal to A. So we have P minus 1 of the P minus 1 of these A. Okay, so finally, what this tells me, knowing that this is an integer, right? It tells me that this, for the whole thing to be an integer, it means the inside the brackets should be divisible by P, implying therefore that A to the power P plus P minus 1A is congruent to 0 in mod P. But then P minus 1 is just minus 1 in mod P, so P minus A is congruent to 0 mod P. And finally, implying that A to the power P is congruent to A mod P, but that's nothing but Fermat's little theorem. So the critical move, a couple of critical things that happened here. So first of all, because P is prime, each of these symmetries create a big cycle, a cycle of length P, but just a single one, right? As a result, we would have the colorings for each one is just A. Second of all, because the number of colorings is obviously an integer, a positive integer, right? So so it means that basically the thing in the brackets is divisible by P here, as we can see. And finally, we were easily able to get the expression, which is basically Fermat's little theorem. So this is a very effective way to prove Fermat's little theorem. In fact, you can advance a similar argument to prove Wilson's theorem as well, or Wilson's lemma as well. In fact, what I would like to do is probably, if I have time, I would like to show that argument, or if not, I would like to prove next, solve, I should say, 2012 AMY 2 problem number 14, which in an implicit way makes use of Wilson's theorem, and that would be our next video, I guess. So hope you enjoyed it, and looking forward to see you guys in our next video.